So in today's video, I'm going to go ahead and introduce L'Hopital's rule, which is a very important application of derivatives when evaluating limits that yield indeterminate forms. And so there's a couple of pieces of terminology we need to be familiar with, one of them being obviously indeterminate forms. But let's go ahead and actually start from the beginning. So L'Hopital's rule, probably butchering that name because it's a very intense French name. I remember it's a very long French name, but that's him right over there. L'Hopital's rule essentially tells us that if we have the limit of some rational function, so the limit as x approaches a of some rational function f of x over g of x, where f of a equals to g of a, right? And that limit, this limit right over here, yields what we call an indeterminate form, which is either 0 over 0 or infinity over infinity. So these two are both referred to as indeterminate forms. Determinant forms. If we have the limit of some rational function that yields one of the indeterminate forms, such that the limit, or such that f of a is equal to g of a, right? Then this limit over here can be evaluated by taking the derivative of the numerator divided by the derivative of the denominator. So essentially it tells us that if we take the limit as x approaches a of f of x over g of x of some rational function, and that gives us either 0 over 0 or infinity over infinity, then this limit can be evaluated by simply taking the limit as x approaches a of f prime of x over g prime of x. So that may sound a bit convoluted, but let's go ahead and do a couple of examples to illustrate this. And we're going to do the particular case with the first indeterminate form of 0 over 0 because it's a little bit easier to understand sometimes. So let's say that we're taking the limit as x approaches 0 of x over sine of x. And if we're to use direct substitution here, well, we know that if we were to place x with 0, then we have 0 in the numerator. And then in the denominator, we would have sine of 0, which would just be 0 over 0, right? So that would be an indeterminate form. And so the way that we could evaluate this then is just by taking the derivative of the numerator divided by the derivative of the denominator. So then this tells us that this limit as x approaches 0 by L'Hopital's rule of x over sine of x is given by the limit as x approaches 0 of the derivative of the numerator divided by the derivative of the denominator. So derivative with respect to x of x over the derivative with respect to x of sine of x, which, what is that going to be equal to? That's the limit as x approaches 0 of, what's the derivative of x? Well, that's just going to be 1. Derivative of sine of x is cosine of x, and then if we use direct substitution, we'll end up with essentially 1 divided by 1, which is equal to 1. So that would be our limit using L'Hopital's rule. And let me actually make a little bit more space because I was underestimating how much space we would need. Okay, so that is how we could use L'Hopital's rule. Essentially, we just need to use direct substitution, see if we end up with an indeterminate form, and then if we do, we can go ahead and take the derivative of the numerator, then divide that by the derivative of the denominator, and then once again use direct substitution to see if our limit works. So let's do that for another example. So the limit as x approaches 3 of x squared minus 9 over x minus 3. If we're to use direct substitution here, we would get 3 squared minus 9 over 3 minus 3, which is obviously 0 over 0. And so we can use L'Hopital's rule again, and that tells us that this limit over here, this limit as x approaches 3 of x squared minus 9 over x minus 3 is going to be given by the limit as x approaches 3 of essentially the derivative of the numerator divided by the derivative of the denominator. Well, what is the derivative of the numerator? The numerator is x squared minus 9, and so the derivative of x squared minus 9 is just going to be 2x, right? Because the derivative of x squared is 2x, the derivative of a constant is 0. And then in the denominator, we have x minus 3. That minus 3 is going to disappear when we take the derivative, and the derivative of x is just going to be 1, so we can write divided by 1 if you would like. And then if we were to input 3, this would just be 2 times 3, which is equal to 6. And so that would be our limit right over there. And you can see that if you actually use a little bit of algebraic manipulation, right, if you factor this, as a difference of squares, if you write this as x minus 3 times x plus 3, divide that by x minus 3, and then we can cancel these two out. And if we were to use direct substitution, then we would get that this limit is equal to 6 as well. So You can use L'Hopital's rule or you can use algebraic manipulation. In certain cases, like this one over here, the previous example, it's a lot easier to just use L'Hopital's rule, but here you could have also used a bit of algebraic manipulation, a bit of basic, polynomial properties. This last one over here, the limit as x approaches 1 of the natural log of x over e to the x minus e. Again, direct substitution yields the natural log of 1, which is 0, divided by e to the 1 minus e, which is just 0 as well. So that tells us that this limit, as x approaches 1, of the natural log of x over e to the x minus e, is the same thing, or is equal to the limit as x approaches 1 of the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator is 1 over x, right? Divided by the derivative of the denominator. We know that the derivative of e to the x is just itself, and the derivative of a constant e is just going to be 0. So this is going to be divided by e to the x, which is equal to what? 1 over x e to the x, or rather the limit as x approaches 1 of that. I should write the limit as x approaches 1 of 1 over x e to the x. And then if we substitute x equals 1, if we use direct substitution, we'll end up with 1 over e. And that would be our final answer right over there. So you can use L'Hopital's rule to evaluate these different limits that may seem extremely difficult at first, and it may not be very obvious how to algebraically manipulate them in order to obtain an answer. But always look out for the indeterminate forms, because L'Hopital's rule only applies when your limit is in one of these two forms over here.